course. This is our 7th webinar, and my name is Kat. I'm the Physics Access Officer for Oxford University. That means that I run all of our events aimed at young people just like you who are aspiring to study physics at competitive universities and at this point in your physics journey are probably preparing to study physics with us in the department that you can see. A few housekeeping things before we get started. You have access to both the chat and to the Q&A. Please keep any questions that you want to ask in the Q&A. That way we're able to get to them. We're able to make sure that we do actually answer all of your questions. Otherwise, they just get a bit lost in the chat. The chat will be for sharing answers to tonight's questions and any general thoughts and comments. You can also use reactions to show us if you're feeling happy, if you've enjoyed something, and we very much enjoy that. Remember, in the chat, don't share any personal information, no email addresses, anything like that. And if at any point you are feeling unsafe, you can email us on safeguarding@physics.ox.ac.uk and we will get back to you and make sure that you are supported in any way that you need. But moving on, I will start by telling you what the PAT test is. For some of you, you are now very well established. For some of you, you might still be a bit uncertain. The PAT is the physics admissions test. It is the required subject test for physics, physics and philosophy, engineering and materials science at Oxford. And your result forms just part of the information that admissions tutors use to decide who to shortlist and invite to interview. To sit the PAT, you will register yourself as a candidate. Your school won't do this for you, and you should all be registered by now. The PAT this year is on screen and multiple choice, and I'll give you a bit more information about that later. This, though, the Preparing for the PAT course, is to help you get ready for that admissions test. Every week in our emails, this timetable is at the bottom. It's always highlighted in yellow to show you where we are. We are at our 4th study focus. Today we're going to be looking at circular motion, and although some of what we're doing today isn't actually on the PAT syllabus, it is absolutely necessary for first year university physics, and it's a great way to practice your problem solving, which is why we do this with you. I will share problem set, our final problem set 4, after today's webinar. As well as tonight's webinar, you can access all of our materials online. This is a screenshot of what that page currently looks like. It's our course material page. You can see there are links to all of the problem sets, to the assignments, to video solutions, to recordings, and I've tried to be quite clear what was in every webinar so that you can go back and find the correct information that you need. We are currently at webinar 7, so you can see that the recording is loaded, but the problems will be live tomorrow. To finish up, before we start on our problem solving, I'd like to remind you that the web link on the page right now, which I share in every email, is the most up-to-date page for all of your access information. So this is the one to check for anything that you are unsure about. I'd also like to remind you that all candidates, wherever you are in the world, will be sitting your PAT at a Pearson Test Centre. The registration for the PAT has closed. It is now closed, so you must already be registered. But if you are registered and you have not yet booked your test, you've got 2 more days to do that. So make sure you book your test slot because they are first come, first served. The PAT is on the 22nd and the 23rd of October. So you've still got a few weeks left after you finish up with us to get your last minute revision bits in. There is a sample test where you can practice using the test platform and you can practice using the calculator. It's not representative of the balance of maths and physics or of the difficulty. It is there to help you get used to the electronic platform. For difficulty, for all of those things, our past papers are your guide. There's a video of a test centre to help you prepare. So if anyone's feeling a bit unsure about what it's going to be like going into the test centres, there's a video of what it's like as you walk through, where you can put your stuff in a locker, what they're going to ask you to sign and show as ID, and all of those things are there. But for now, that is the end of my brief introduction to the PAT. This evening, we are joined by Justin, who ran our tricky problem-solving session 2 weeks ago. I'm sure he will be raring to go. He's going to be taking you through circular motion. For anyone who has not met Justin yet, here he is. Justin, everyone is excitedly using the reactions. They are ready to go. My briefing was much shorter because they all have to have registered by now.
Lovely. If anybody's on YouTube, might there be people on YouTube?
Absolutely, yep. It
Get
is
over
live and
here.
in action.
Yeah,
So anyone on YouTube, you've probably already been sent the link. So please come and join us. Follow the Zoom link through your emails, and then you'll be able to share answers and we'll be able to interact as we go.
I really want to see those answers today. We're going to start with a few more tricky problems because those went down really well. And then
Absolutely.
we're going to get into the circular motion, like the proper physics, nuts and bolts in there. So let's see if I can share the PowerPoint for today. And hopefully people will tell me if this is not working.
Lovely. And in the chat, I am going to share the link to your problems today, problem set 4. So that is now in the chat. I always get messages at this point from people saying that the link doesn't directly work. I think this is internet browser related. So if that link that I've posted doesn't immediately work, A, I've already sent you it by email, but B, you can also go to our course material page and it's linked. It'll be the final link because we're right at the bottom of the page.
Perfect. So today, the first warm-up problem, it takes 20 minutes to fill the bathtub if you just run the hot water tap. It takes 15 minutes if you just run the cold water tap. And when the bath is full, it takes 10 minutes to drain the bath if you remove the plug. So if both taps are running and the plug is removed, how long will it take to fill the bathtub? Answers in the chat, please.
Justin, would you like me to make them only come to us?
Yes, I think so. Let's not have spoilers.
Okay, I'm going to reset the chat so it's all going to be coming through to hosts and panelists now. And what that means is that you won't see all the answers coming in, but we will. And if you've got any questions, pop them into the Q&A. We can help out there.
Okay, I am seeing lots of people getting the correct answer straight off the bat.
Massive variety though.
Yes, so too low is nada, and too high is a FIFA. Miles, you are miles too low. Everything else I'm seeing so far. Oh, wow, what's this? Felix, far too low. Isabel, too low. Everything else is looking good. So maybe this is not a tricky enough question for you. So if you weren't here last week and I didn't spoil the triangle one for you, I think that's the next question. I'm not going to spend a lot of time on it, but move on to that question. If I didn't spoil it last week. Isaac, that is too low. Ileana, too low. Albert Chang, too low. So if I've not told you you're too low or too high, assume you've got the correct answer. Isla, you've not even included units. I think there's 2 Islas today. Or maybe the same person logged on twice. Thank you for the units. You are too low. Nado is too high. Tabitha, you're the second person to say that number. So I'm wondering what's going on to get that. Too low. Isabel, too low. So when we look at the formula for calculating this, you are immediately going to recognize the format of this because this is essentially a rate question. So we did, I think, a rate question in the last session where a couple of people were painting my house, perhaps. I don't remember if that was in there. But there we had 2 people working together. So when that happens, we need to essentially work out the rate that each person is working at, and then we add their rates. Here we've got 2 things working together, the 2 taps. Adam too low, Lucy too high, Sophia too low. Fiona, units. Ellen, too low. Isabel, too low. So we had a flood of correct answers, but most coming in now are incorrect. Gabriel, too low. Fiona's now correct. Hassel, too low. Mahika's correct. So again, we're adding rates, but now we've got something working against us. So we need to subtract that rate, sorry, as we do this. So the way that we do this is we look at the time that it would take. So to get the total time, you're doing, ooh, this looks like I'm almost adding resistors in parallel until I start subtracting here. And indeed, this is what's going on in a resistor problem. It's the rate of flow of current. And I've got two resistors in a different branch working in parallel to let current flow through at different rates. And then I want to know the overall rate when I add them together. So this is essentially the way that we add rates, and then we just have to subtract. And now it's just math at this point. Joan can't find the question and answers. Do we need to repost the link, Kat, perhaps?
I think they're looking for where the Q&A on Zoom is
Oh, okay.
rather than our questions and answers. So I'm just typing an answer to
Lovely.
them.
Okay. All capacitors in series, yes, but not everybody will have done capacitors just yet. Or you can be looking at adding springs. They work in a similar way depending on whether they're series or parallel as well. So you can do this in our head. Lowest common denominator, boom, 1 over 60, 60 minutes, 1 hour. So very briefly, this caused a lot of pain to people 2 weeks ago because they just assumed 9, 16, 25. Ah, that looks like Pythagoras. Of course, Pythagoras is 3, 4, and 5 in terms of the lengths. If you were to actually get a ruler and maybe a compass and try and draw out this triangle, then you will realize that actually it's basically a straight line. So H must be 0. So lots of people spent quite a long time getting frustrated, and I felt a little bit guilty because that was kind of a trick question rather than a tricky question. But let's move on to the next genuine question. And this one might seem a little familiar if you remember the battle between the pirate and the ninja from 2 weeks ago. So a family exercises their dog in this following way. The parents sit on a beach while the children walk to a distant rock, calling to the dog as they walk. Parents and children alternately call the dog, who runs from one group to the other and back again. The children then walk back to their parents, still calling the dog on the way back. If the dog travels at a constant speed and the children also at a constant speed, calculate an expression for how far the dog will run in total, given that the distance from the parents to the rock is d. So some algebra for you.
I really love that somebody just messaged us straight away, Justin, and said, but how are these questions made?
Yeah, so some of them I discover and repurpose. Most of them I do actually. I've collected a lot. I changed some of the wording. Okay, so some answers coming in. Let's have
Yeah,
a
we
quick
got quite
look.
a few. I'll go away.
Okay, don't include units. This will confuse me if you include units here because it's an expression. It's not a numerical answer. But Poppy, I believe that is correct. Ava, too complicated. Colton's correct. Evie's correct. Tanishka, no. Struggling with a name here. Dinanda? I hope that's not butchered terribly, but you're correct. Ishita, no. Can we assume the dog travels all the way to the person before another call? Yes, make that assumption. The dog is like the parrot in the previous one. Mal, no. Alistair, no. Felix, no. William, no. Lots of people getting the same wrong answer here. You're on the right lines. but you've just missed something. Isaac, no. Clara, yes. Joan, yes. Oh no, it's going too fast. Um, okay. Nafim, no. Cara, close but no. Esther, yes. Andrew, no. Lillian, maybe if you use the correct terminology that I've given you. Fabian, no. Jay, no. Nathan, no. Wayne, yes. Liana, no. Fiona, no. Hassel, yes. William, no. Ishita, yes. Megan, yes. Brian, no. So one thing that people can be doing is a little bit of dimensional analysis on this. When you get your expression, check that the units will give you meters. If they don't, then your expression cannot be correct. So sorry, I've missed a few people out. I think we're back to Ishita, who now has it correct. Megan, correct. Brian, no. Alistair, no. Timothy, no. Mahika, no. Paris, no. Yes to Tanishka and Lillian. No to Mahika. No to Mal. Yes to Emma. Okay, it's time to stop dropping some little hints in here. So remember, the dog is running at constant speed. So when we had the parrot flying at a constant speed, the key thing was to work out the time that it is running for. If you can find that time, you just multiply it by the speed to give you the distance. So Emma's correct. Fiona's correct. William is correct. Andrew's correct. Pierre, correct. Zarin, correct. Okay, I think that was a good enough clue, sorry. Um, so the mistake that is quite common is a few people are missing out a factor of 2. We are traveling there and back. So I think other than the factor of 2, everyone else is now getting the right answer. So the time is obviously distance over speed. So we're working out the time it takes for the children to walk to D and back again, to the rock and back again, divided by their constant speed, VC. So there's the time. Now we just multiply it by the dog's speed to give us our expression. Hopefully that's reasonably straightforward. Most people, I think, got there. Isla, you can't put in the answer now after I've revealed it. That doesn't count. Let's have a look at the next question. Let's go to classic probability. We did a few probability questions last time. In this example, we have 3 cards and they are hidden under a cloth on a table. We know that one card is white on both sides. One is black on both sides and the other one is black on one side and white on the other. So I now shuffle them up and randomly select a card from under this cloth. It turns out that this is white. What's the odds that the other side is also white? So correct answers coming in. Dineda, Ava, Isaac. Oh, it's going so fast. I saw another one that I've missed. Ryan, Angelica.
It is going really fast. I'm trying to keep an eye on it in case anything comes through, but I'm definitely
Esther.
missing a couple today.
Okay, Eve, don't give me a calculation, just give me an answer. Lots of wrong answers though on this one. Ishita, I know I have missed somebody who gave me the right answer early on. So if you want to just pop in your answer again. Billy's correct. Gracie's correct. Ooh, Rodrigo, Fiona, Joan. These are all the correct answers so far. If I've not called out your name, you maybe need to rethink this. Brian's correct. Submit the answers in the chat, Olin, and hopefully I can keep up. Timothy's correct. Cara's correct. Isaac's correct. So if you've said a half, which a lot of you did, that is incorrect. Nafim is correct. Uh, Chinmay's correct. Maiko's correct. Okay, Lillian, you've given me 2/1. That's just bonkers. Tanishka's correct. If you have said a third, you are incorrect. Lillian's correct. Ellen is correct. Owain is correct. Freddie's correct. If you have said a quarter, you are incorrect. Fabian's correct. Wolfstan's correct. If you have said a ninth or any, no, I'll just say if you've said a ninth, you are incorrect. Adam's correct. So this is related to the Monty Hall problem, in a sense. Mal is correct.
I'll share a link to that in just a second, just answering a question in the Q&A.
Okay. Alina's correct. Miles is correct. Faris is correct. Nathan's correct. We're getting quite a few coming in now. Question 5 is not possible. There isn't a question 5. There's a question 1 of the next section. Zarin's correct. Thomas is correct. Let's have a little think about this. So if I have selected a white face-up card, it is actually more likely that the card is the white card, because half of the time the white-black card won't be an option because it will have its black face up. So if I imagine running this twice and in between the two runs, I flip over all of the cards, so we have all of those options out there, then there will be 3 white face-up cards and 3 black face-up cards. And 2 of those white face-up cards are going to be the card that is white. So even though it's random, the very fact that I have selected a white card, it is more likely that I have selected the white card than the white-black card. So lots of answers coming back in now. Mahika, Ben, and Alistair all correct. So this means it is a 2 in 3 chance that the other side is also white. So very similar to the Monty Hall problem, which is, a classic game show. You get to the final round and there's 3 doors. Behind 2 of the doors is a goat. Behind the other door is a car. And you're motivated to try and win the car. Even though insurance prices at your age will be through the roof, goats come with a lot of their own costs. You've got to feed them, you've got to look after them, vet bills. You can't just eat the goat, you need to fatten it up first. You can maybe get a little bit of milk out of it, but you don't really want the goat, okay? You want the car. So you pick one of those doors. Call them A, B, and C at random. Let's say that you pick door B. The game show host, who happens to know where the car is, then opens door A and shows you a goat. Ah, he says, it's very fortunate that you didn't choose door A, because if you had, you would have won the goat. Now, do you want to stick with your original choice, door B, or switch to door C? And most people will go with their gut and they think this is good news. Yeah, I didn't pick door A, so my odds have improved. It was 1 in 3, but now it's 1 in 5. But whichever door you picked, the game show host could always open one of the other doors and show you a goat. So that doesn't actually change your odds, because he can always do that. So the odds that it's changed is the other two doors. Between them, there was a 2 in 3 chance that there was a car. He's just shown you the other door which doesn't have a car. So now that 2 in 3 chance has all gone to that door C. So actually, you will double your chances of winning by switching. So let's have a look and go from the fun things into the, physics. But I think physics is a bit of fun. Before we get into the problem,
Always.
I'm going to try to teach you something. There are 4 things that I learned at university that I wish I had been taught at A level. And I'm going to show you 2 of them. This first one is called the unit circle. Some of you may be familiar with this from maths, and essentially it's useful for you in maths to memorize the common sine, cos, and all of the other trig values for nice angles, 30s, 45, 60, 90, and the other ones, because they come up quite a lot. So you might have committed this table to memory, but you don't need to. There's one number that I remember, and that's that sine 30 is a half. Everything else I am going to work out, and I'm going to show you how to do this. So obviously we need to know definitions of tan and the other functions, because that just means that if we've got sine and cos down, then we can fill in the others by doing these calculations. So hopefully we know these definitions. It'll be strange to be doing the pat if you don't. So let's just try to figure out these values for sine and cos. All we need to do, well, 3 things. Polar coordinates. Polar coordinates are incredibly useful, particularly when we're doing things that have circular symmetry, things moving around in a circle. There's also spherical coordinates, and there's a couple of different kinds there, those that have spherical symmetry and those that have cylindrical symmetry that you could use. Pythagoras, of course, we know, and symmetry. So let's apply these principles and see how they work. So I have drawn a circle on the XY axis, and I've labeled a point P. Now, traditionally, using Cartesian coordinates, this point P would be, its location would be given by X and Y. But there's another way that we can express its location. We can talk about its distance from the origin. So we can label this distance R. And we can talk about the angle that you make going anti-clockwise from the x-axis. This is what polar coordinates are essentially. So we can label this position P with a number R, the length from the origin, and an angle going anti-clockwise from the x-axis. Now, if we want to switch between these 2 coordinate systems, this is quite easy to do because we've actually got a right angle triangle. So we can just use some basic trigonometry to do so. So if I've got r and theta and I wanted to know what x was along here, well, that's just going to be r cos theta. And y similarly is going to be r sine theta. Beautiful triangle. I could go backwards the other way if I wanted to. It's a little bit trickier, but it's nothing too hard to do. But there's a property about this circle. It's called the unit circle because I'm making this length r equal to 1. So by applying Pythagoras, we can now say that our hypotenuse, which is 1, is going to be equal to x squared plus y squared. But substituting for x as 1 times cos theta and y is 1 times sine theta, we get this beautiful equation. 1 is equal to cos squared plus sine squared. This is just Pythagoras in polar coordinates. Absolutely beautiful. So how are we going to use this to try to work out what the values of cos and sine are for the common angles? Let's start with 45 degrees because this has the most symmetry. At 45 degrees, we know that this angle up here next to P is also 45 degrees. This is 90. So this length X and the length Y are also going to be the same. That means that I can substitute Y1 as X1. So when I do that, I just have 1 is equal to 2 lots of X1 squared. Solve for X1, root 2 over 2, or 1 over root 2. You can write this in many different ways, but pretty straightforward. Then I can also solve these other angles. So 135 degrees, 225 and 315, because I can just draw this diagram and I can see that y1 is going to be the same, but now x is going to be negative because it's on this side, this quadrant, and so on. So I can fill in these values for all of the multiples of 45. Maybe not the 90s and not the multiples of 45, but the lines that I've drawn there. So we see that cos 45 is the same as sine 45 from symmetry, and we can fill in a load of values. Let's have a look at the next one. Let's go for 30 degrees. So at 30 degrees, x is going to be larger than y. Just looking at the diagram, hopefully that's nice and clear. But this is the one that we've remembered. We know that sine of 30, which is y1, is equal to a half. So y1 is a half. So if this is a half, we can work out what x must be, which is cos of 30. Because we know Pythagoras tells us that the sum of the squares is 1. So we substitute for a half as y1, and then we just rearrange to discover that x1 is root 3 over 2, which is cos 30. So if I wanted to go to 60, well, I can just reflect my 30-degree line in this 45-degree dashed line, and I can use symmetry. I could try and work it all out again if I wanted to, but let's just use symmetry. Reflecting it there, and we can see that the values of x1 and y1 have essentially swapped position. So sine 30 is equal to cos 60 and vice versa. And then we can just reflect this in this y-axis if we wanted to work out what 120 would be and 150 would be. We just put in a minus sign on the x's, the y's stay the same. And while I'm up here, let's have a look at the angle of 0, 90 and 180. So at 0, the line is just along the x-axis. So clearly, the coordinate that the unit circle makes on the x-axis is 1, 0. At 90 degrees, it hits the y-axis, so it's 0, 1. And at 180 degrees, it's 0, minus 1. So we can now completely fill in our table. And if we do this, maybe you don't want to do this derivation every time. There is another little shortcut to help you remember things because there's a nice little pattern that we can find. If we write everything over the square root of 4, then the pattern becomes 0, 1, 2, 3, 4, and down on the other side, 3, 2, 1, 0. And for the causes, we start high, 4, 3, 2, 1, 0, and then we come out the other end, minus 1, minus 2, minus 3, minus 4. You don't often see it written like this, but this is a nice little way, and you can kind of see the symmetry quite clearly with this. But being able to use the unit circle, polar coordinates are very essential, and of course your trigonometry and Pythagoras, this is where this comes from if you ever forget this and you get stuck. So I didn't learn this until I got to university and my mind was blown. I'm seeing lots of mind blown faces, I think, or maybe that's just one person repeatedly hitting that reaction. Who knows? So another thing that I learned at university that I wish I'd have learned at A level is that SHM, simple harmonic motion, is the same thing as circular motion. It's just viewed from a slightly different angle. And it's also the same thing as a wave, your sine cos waves. There's a nice little animation that demonstrates this. Let's look at the one on the right first of all, because this is a little bit easier. So the black dot is an object doing uniform circular motion. It's going around at a constant angular velocity, tracing out the path of a circle. The red dot is its Y projection. So if I was stood side on over here somewhere, just looking at this black dot, all I would see is the red dot. I would see it bobbing up and down. And you'll notice that as it bobs up and down, it travels quickest through the center, slowest at the ends because it has to change direction. This is describing simple harmonic motion. So if I were to have a mass bobbing up and down on a spring, for example, that's a classic example of something that does simple harmonic motion. But there's so many things in the universe that actually do this and behave like this. Atoms, molecules vibrating, for instance. That's what's going on. And if I were to trace its position, its Y position as a function of time, this is what you can see in this chart. So as time moves on, we are doing this periodic motion. We're tracing out a sine wave. So all of these things are the same. The diagram on the left just demonstrates the X and the Y components at the same time to show you that there is a phase change. So where the Y one was doing a sine, the X was doing a cos. So it's lagging or leading by 90 degrees, essentially. So something going around in a uniform circle at a constant angular velocity. You look at it from side on, it's something just bobbing up and down in simple harmonic motion. One of the most surprising results, if you've done simple harmonic motion, is for the time period of a pendulum, because it's got 2 pi in there. Something that's just swinging side to side. Okay, it's tracing out an arc of a circle. Why would a pi be involved? Because if you look at it differently, it's actually going around and doing a full circle. If you can imagine that. So hopefully you'll take that with you. And once you've made that connection, you can use the same mathematics. This omega, the angular velocity that appears in circular motion, simple harmonic motion, in the wave equation, if you're writing your wave equations with omegas in them, it's the same omega. So last week, my year 13s were doing this experiment, the classic whirling bung experiment. So you get a mass on the end of a piece of string and you thread this piece of string through a frictionless tube. You hang another mass below it and you try to like swing it Gangnam style over your head to get into a rhythm where it's, you know, traveling in a horizontal circle and somehow somebody's there measuring the distance and timing the time period for rotation to try to show the equation for centripetal force is valid. However, this is an absolutely terrible experiment. So draw yourself a clearly labeled diagram and tell me with this diagram why it's impossible to get the string horizontal. And in order to get it horizontal, which is the aim, tell me how fast you would need to be spinning this. How can the pendulum string travel fast if it is exactly horizontal? You're going to need to give me a little bit more. Okay, Tanishka, I like that explanation. Thomas, correct. Can you explain why? Oh, I've just missed one as well going up. That I thought was quite a good explanation. These ones will take me a little bit of time to read. So I'm going to miss some of them. Albert, yes. Can you explain why? Christian, true. Ava, very detailed. I think that's correct. Okay, lots of people giving me the correct reasoning and the answer here. Hopefully, you've drawn a good diagram, and the diagram should make it perfectly clear. So let's have a quick look at my diagram. So in this scenario, this is the bung. It's below the horizontal currently. So the tension in the direction of the string and the weight of the bung are the only two forces acting upon it. So for this to be going around in a horizontal circle, we need the sine component of the tension to balance the weight. And then we're left with our resultant force. The cos component of the tension would provide the centripetal force in this case. So we can go through the motions and we can start writing these things out. And then we can combine these equations and we'll get a little tan theta term coming up to work out the angle. So if we want tan theta to become 0 and r is fixed and gravity is fixed, in order to make it 0, v needs to tend to infinity. But hopefully we can see this from the diagram, which a lot of people in the chat have noticed. We need to have some component to cancel out the weight in order to keep this in vertical equilibrium. So for there to be a component, there needs to be an angle, essentially. So that's why this can never be horizontal. The faster you go, the closer to horizontal it will become, but you will never be able to actually get there. So it's a terrible experiment that most people, most students will do. I mean, I have great fun doing it, and I enjoy doing it because, not because of this, but because of how tricky it is to get decent data. And, you know, that's a skill. Trying to problem solve that in a practical sense for how you can get some decent data out of this equipment takes some smarts. So, next question. Let's assume that the Earth is a perfect sphere, radius 6,400 kilometers, and it is spinning on its axis through the South and North Pole. If a person stands on some weighing scales at the North Pole and the scales were to read 800 newtons, let's imagine that they teleported to the equator. Would the scales read the same value, less, or more? And if different, the follow-up question is, what is that value? What's that difference? Thank you, Mahika. Enjoy my explanation. I do try. So I think we have all three possible answers given. So somebody's correct. I'm not going to say who's correct, but stick with your conviction and tell me the value. Ava, you're very close in your value to what I've got. But this happens every year. I doubt myself. I assume you're using 9.81 for G. I think I was. Nada. No. Okay, Ava, use 9.81 and then we might agree. William, yes. Joan, yes. Denada, are you using 10? Don't use 10, please use 9.81 to agree with me. Poppy, close. See, now I'm wondering, was I using 10? Ava, I now agree with you, although my answer's to two sig figs. Uh, okay, I agree, I think, with Isaac. Someone else has just gone off the screen. So the answer is less. Why less? So Mahika's given me, so the person at the equator would be experiencing more force, as there is a higher radius and higher linear speed. So it's less, but not that small, Zarin. Timothy, Tabitha. Fabian's correct. Poppy is correct. Joan says, at the equator, the Earth's spin makes you slightly lighter on the scales. That is true. But why is that true? Let's have a look at some of the spoilers to work this out. So at the poles, there is no centripetal force. Essentially, over a day, you just rotate on the spot. But at the equator, you are tracing out a very large circle, a circle of radius 6,400 kilometers over the course of a day. So you are traveling very fast, but you're changing direction. So you are always accelerating. There is therefore a centripetal acceleration. So there must be a centripetal resultant force. Christian, converting to kilograms. Oh, I've not done that conversion, so I don't know. But Zarin and Timothy are now correct. Thomas, it's a bigger difference than that. So there are only two forces acting on this person. They are your weight, which is acting towards the center of the Earth, and the normal reaction force. The thing that provides the normal reaction force is the scales that you are standing on. And now there's a Newton's third pair. It is not your weight and that normal reaction force, because those are forces of a different type. Your weight is not a contact force. So the Newton's third pair with that is you're pulling up the Earth, the center of the Earth, towards you. But there is a Newton's third pair acting on the scales. So you are pushing down on the scales in reaction to the scales pushing up on you. And it's this reaction that the scales are going to measure. But if you are moving around in a circle at the equator, then this means there must be a resultant force acting towards the center of the Earth. So therefore, the upward force on you from the scales must be less than your weight acting towards the center of the Earth. So we can work out that difference because you can work out what the centripetal force must be acting on you. So that's the reason why it is less. It must be less. Lots of numbers coming in. Miko's correct. Christian is too low, but units, come on. Lillian's too low. Ishita, I think, is correct. Miles is too low, but not Miles too low this time. Give it as newtons, please. Don't make me try and go to a calculator. I don't want to. Varzana, close. I think you might be using 10 instead of 9.81. Isaac is too low. So here's the diagram. Hopefully you drew your own diagram. So what is the difference? And if I've told you that you're correct, the follow-up question is what would you weigh on some scales at Oxford? And I will tell you the latitude of Oxford is 51.8 degrees. If you do geography, then you know what that means. If you don't, take an educated guess. Pierre, units. Okay, are people answering me the Oxford question? Ava, I think you're onto the Oxford one right now. In which case, I think that's correct. Still people giving me answers in kilograms. I don't want answers in kilograms. Stay in newtons, please. So let's move us all on to Oxford. Let's have a look at uh, the resultant forces for this one. So our weight minus the support force at the equator gives us the resultant force, which is our centripetal force. Let's get rid of omega and turn it into time because we understand that it's 24 hours, 86,400 seconds. So our support force is our weight, just taking our mg here and turning mass into weight, rearranging that. Now it's just a case of substituting in the given quantities. If I want to work out the change, the difference from my weight, then I can neglect this weight and I'm just interested in this bit. So this is just the difference. Few answers coming in for Oxford. So Joan, I think that's correct. I'm going to want one decimal place to check your answer for Oxford, please. So plugging in the numbers there, I got 2.8 newtons. So moving on to part C, T450. So is that a Terminator model? I don't know. Correct though. So find the value in Oxford. So Isaac is too low. Probably the same answer is Dinarda, also too low. Joan, it's gone off my screen, please. Type it again. Owain is too low. Joan, I believe it's correct. I've only got an answer to one decimal place. Too low, Dinarda. Nathan, there's no units. Wolston, no units. Colton, correct. Ryan, too low. Nathan, I assume you're giving me the difference rather than my weight. But no, that difference is too high. Okay, Wolfston, don't annoy me with complicated units. I know they're SI base units, but it's late. I don't want to have to do more thinking than I need to. So this is a little bit of an exam hint for you. Do not annoy the examiners. Just give them what they expect. If you make them think and your answer is borderline, so that means they may give you benefit of doubt or not good enough, and different examiners will judge it differently. If they're in a bad mood, that's all I'm saying. Alina, no, too high. Tabitha, give me one decimal place. Timothy, yes. Okay. Let's drop a hint. So when I first did this, I realized that things weren't working out because there are three forces acting on you at Oxford. And there needs to be three, because if there's just two, and these are in opposite directions, then the resultant force is going to be radial towards the center of the Earth. But the circle you are tracing out is this dashed line. You need your resultant force to be pointing towards the center of this dashed line. So just with your weight and the support force, that's not going to cut it. Once I realized that, I thought, oh, that's a little bit odd because I don't notice this friction. But if I was on a lake, a frozen lake in Oxford, and it was spinning around and there was no friction, I would slide to one side of that lake. Very odd. So where are we at? Timothy, you are too high. Fabian, that is too much of a difference. Evie, there's more of a difference than that. Wolfstan, thank you for appropriate units now. Too low. Maiko, too low. So, can I explain this third force? Let's start off with imagining that there were just these two forces. I'm just essentially going to repeat myself again because I can't think of a better way to explain it than the original way. So if I just had my weight and my support force, which of course is at 90 degrees to the surface, my normal contact force, then the resultant force of these two vectors must act along this radial direction. So that would give me a resultant force pointing probably towards the center of the Earth. But I'm not spinning around the center of the Earth. Otherwise, I'd pop up down here somewhere and then back again. So the axis, the North Pole is up here that I'm rotating around. I trace out a circle that goes around this dashed line. So it has this radius circle from here to that point. So that's why two forces isn't going to cut it. So what else could be a possible force? The only other thing I can think of is friction. So when we add in friction, that's going to be acting in this direction because without it, I would actually slide towards the equator. So that takes a bit of conceptual thinking about for why that would happen. But if you've ever been to a pizza restaurant and watched them make the pizzas and they spin the dough above their head, that dough spreads out. As it is spinning, some people will call it a centrifugal force, but I avoid that word like the plague. But the bits of dough on the edge are pulling outwards, stretching the dough. You are like an edge bit of dough. And as you get spun, you want to move outwards. So in this case, you would be sliding towards the equator on there. Let's start going through this. I need to keep a track of time, actually. Oh, we're doing half an hour left. That's fine. So, where's my animations and why aren't they doing anything? Oh, all at once. Okay, like a good bus. So, let's start with this force diagram in the bottom right. So, nice big diagram. That's what you need when things are going to get complicated. And we can resolve it vertically and horizontally. So vertically, we know that our upward components are s sine theta plus f. In this case, we're going to get a cos theta if I were to put in a little triangle in here and chase the angles around. So those are my upward ones. Those must be balanced by this downward component, mg sine theta, because I'm not moving upwards or downwards. I'm moving horizontally around this circle. So those are balanced, and I can simplify that by dividing through by sine theta or cos theta. Yeah, I divided through by cos theta to do that. So then we have a look at the horizontal. So we've got two things providing a horizontal force inwards, our component of our weight and a component of the friction, and we're subtracting the component of the support force. So that's what we've got on this side, adding those two terms pointing to the left, subtracting the support force. And that's going to provide our centripetal force, the resultant here. So that's going to be our m omega squared r. And we can convert that omega into time at some point. That's the physics. We've got these two equations. Now we just need to do the math. So when I do the math, I'm also going to get rid of little r or big R. Where's this R? Let's get rid of that little r and turn it into a big R, because this is the information I've got. I've got the radius of the Earth. And when I do this, this actually simplifies this equation because I get a cos theta term. So now I can divide everything by cos theta again, and I'm just left with this 1 tan theta term. And then if I wanted to, maybe I could substitute for F in here, or I could rearrange for tan theta and substitute for that, whichever's going to be simpler. At this point, it is just math. So if we skip over a little bit of the math, we arrive at quite a nice expression, or a familiar expression. So it's what we had before, but now I've got a cos squared theta. So when we went to the equator, theta was 0, or was it 1? No, it was 0. So cos of 0 is 1, square it, it's still 1, and we get the same term that we had at the equator. And if we didn't get that, we would know that we'd made a mistake. So now we're working out something that's more general, and at the equator we had a special case. We just plug in the numbers again. So plug in those numbers, and I've got 798.9 newtons. Tricky question. But all of this physics you should be able to do. The tricky thing is realizing that you needed this extra force. From that, it's all the problem solving that you've done before. Clear, large diagram. Resolve forces, break it down into components. Then it's just math. If you're struggling with the math, this is recorded. Those are the steps that I missed out. There's a nice little trig identity in here, tan squared theta plus 1. You can get a nice term there. So 1 over that gives you your cos squared theta.
We've got a couple of questions in the Q&A, just to warn you, Justin. A few people asking where that cos theta comes from and why it's not mg cos theta.
So I think if I just pause on here for a moment.
Yeah, I think actually that is absolutely all that is needed. That's great.
Okay, so we can see these steps. Is the reaction and the weight at the same line in Oxford? When you say the same line, they are in opposite directions, but they are, I suppose, collinear, if that's the correct word. So yes. All right, let's move on to going back to the equator. So now we realize that we weigh less at the equator. If the Earth was spinning faster, you would weigh even less. So let's get a little bit real. The Earth isn't spherical. It's an oblate spheroid. So this means that it's thicker at the equator than at the poles. So let's take that fact that it's thicker at the equator, and this actually gives rise to two effects that will affect your weight. What are those two effects? And now that we're being real about it, would you weigh more or less than we had calculated? So a little bit of an open question. tell me the effects as well, not just whether it's more or less, because that's like a 50-50 guess. Okay, Evie is giving me both effects. Okay, Lucy, you need to explain there's a missing step for why that radius, the change in radius, matters. Okay. Whoa, loads of answers coming in now. Far too fast to read all of them, so I'm going to just try and pick out a few of them if I can. So most people are telling me that we would weigh less. Oh, the Coriolis force. I think the Coriolis force or the Coriolis effect comes up in the next study session. So I remember when we were doing these face-to-face in Oxford, and somebody was complaining that hurricanes aren't to do with physics.
Yeah, there is one. Our undergrads are going to take them through the questions. You've got a
Yeah.
couple of questions about friction in the Q&A, Justin, because I know you're monitoring
Oh,
the
lovely.
chat, so I'm just interrupting you to let you know. Someone asking where the friction in the equator is, and someone asking where the friction comes from in the Oxford case, which I think is
Okay.
probably the same explanation.
So in Oxford, I assume that you are stood on the floor. So the friction will be between the floor and your feet. At the equator, you do not need friction because you are already on the edge, as it were, of the Earth at the widest part. And again, this is to do with hurricanes because the fun fact about hurricanes is above the equator and below the equator, they rotate in opposite directions, anti-clockwise or counterclockwise. I forget which, but I can derive it. And if you can do
Thank you.
physics, you can derive that as well. So lots of people pointing out that the radius is greater. True that, but what effect does that have? Well, it has two effects. If we know Newton's law of gravitation, that means that you are now further away from the center of mass of the Earth. So therefore, gravity is slightly weaker, which means that your genuine weight will have decreased. However, if you're now in a wider circle than what we assumed, but you're still going around in a day, that means you're traveling faster. So your centripetal acceleration must also increase, and therefore your centripetal force must increase. So these two effects, when you think about them and you draw out the diagram, you realize that these act together. So both of these effects mean that you would weigh even less at the equator. Interesting question. Why is the Earth not spherical? You would think you look at the moon. Okay, it's got some craters, but essentially it's spherical. And the Earth has much stronger gravity, like 6 times stronger gravity than the moon. So it should be able to pull the Earth into a better sphere. It's not a sphere because it is spinning. So it's going back to that pizza analogy. So the points on the Earth are trying to flee, I'm not going to say it, away from the center. And when you get to the equator, they can't flee further away from the center than just bulging. So you get this this bulge at the equator, and then the poles are closer in. So those would decrease your weight.
I like the shocked faces coming through.
Hmm. Um,
You've just got one person asking about forces opposite to friction. So now that we've happily covered friction and covered that centripetal.
so the Newton's third pair to friction.
I think that's what they're asking. Yeah.
So you pulling the Earth the opposite way to the Earth pulling you. But
Yeah,
considering,
that's what I
yeah,
was thinking. It's just sometimes these answers, when typed, don't quite come through.
no. Um,
Thank you.
so we're we're talking about the moon a little bit. So the moon does actually rotate. It rotates once every 28.3 days, 27.3 days, a lunar month, essentially. So this is why you only see the same side of the moon all of the time, because the moon is what we call tidally locked with the Earth. So it is spinning on its axis at the same rate that it orbits the Earth. And there's fascinating physics for why that happens. But the moon used to spin a lot faster, but now it has slowed down. And actually, the moon, Newton's third law coming again, is slowing down the rotation of the Earth. We can go back through fossil evidence and actually find out that days 4 million years ago were only about 20 hours long. So the Earth was spinning a lot quicker. So my next question, let's travel even further back in time. How long in hours would a day be for somebody at the equator to just float, to be weightless at the equator? Okay, Colton has already got onto this question with the correct answer. Okay, T450. Are you making assumptions that I'm obese? Hmm. I'd say overweight. I wouldn't classify myself as obese yet. Ava, correct. What's the mass of the person? Fabian. Mass cancels out. If I've not given you the mass, you probably don't need it. Um, Alina, you'll be surprised. Dinadia is correct. Hassal is correct. This is actually a much easier question than the Oxford question. I saw an advert the other day for some like weight loss place where they were advertising that if you call this number, they will tell you your BMI for free. How hard is it to take your mass in kilograms and divide it by your height in meters squared that you need to phone somebody up to then tell you your BMI? Uh, sorry, Adam, meters per second. Are you answering the next question? The answer to this question should be in hours. Um, Hours, please, not seconds. Evie, hours, not days. Tabitha, too short. Pierre, correct. Isaac, too long. Do we need radius? Probably. Let's go back to a spherical Earth. Timothy's correct. Adam is correct now. Grace E is correct, as is Brian, Owain, Lillian. Um, okay, reality check. It's going to be less than 24 hours. Ryan's correct, as is Lucy. Tanishka, that is far too low. Next question, Denadia. I believe that's probably correct. Isaac's too low. Sam is too high. The radius is 6,400 kilometers. Don't give me a calculation, please. Isaac's correct, as is Maiko. So this one's much easier because you only need to consider one force. This is the expression that we previously derived. However, if we are weightless, what does that tell you about the support force? Isla's correct. Zarin's correct. Alistair's too low. Evie's too low. Gabriel's too high. Megan's correct. Mahika, no. That's not what it tells you about the support force. EV's too low. Ooh. There is a part B to the next question, but I don't have it on my slide. I was very confused why I put part A. Wolfstone, probably correct. I preferred it in hours, not the minutes. Tanishka, yes. Okay. If the day was shorter than this, would we be thrown out from the Earth? Essentially, yes, you would. So, lots of people giving me the correct answer now. I'm trying to move on to the next one. So, if we are weightless, this means the support force goes to 0. And then we can see that the masses cancel out. And we can just rearrange for t and substitute in the things that we know. So 2 pi root r over g gives you, surprisingly, only 1.4 hours. That doesn't seem that fast, but at the equator, you would be floating at this point. Imagine going there for your holidays. You don't need the Dead Sea. You could just float in the air. Amazing. Why does it go to 0? So this is about what we mean by weightless. I was asking my year 13s just a week ago, what's going on with those people on board the International Space Station? They're going around in microgravity. Why do they experience weightlessness? And of course, I get the common answer that, oh, there's no gravity on board the ISS. There's no gravity in space. So I ask them about the moon and what makes the moon orbit the Earth. Oh, gravity, they tell me. Well, I say, where is the moon compared to the International Space Station? Hundreds of times further away. So gravity should be, what's that, 10,000 times weaker if it was 100 times further away. But it's big enough to have an effect on something like the moon to make it orbit the Earth. Gravity on board the ISS, I don't like it when they call it microgravity. It's like 99% of the gravity that you feel on board, sorry, on the surface of the Earth. So you definitely have weight. The key thing is you experience weightlessness because there is no contact force. It feels like you are falling because you are falling. And this is because the tin can that you are falling in is also falling at the same rate. So if you imagine that you went in an elevator, and if it's a nice safe elevator and you go up and down, sometimes you feel heavier when it accelerates upwards, or you feel a bit lighter when it accelerates downwards. If somebody were to cut that cable, you would now experience weightlessness. This is what it would be like to be on board the ISS. But rather than going around orbiting, having a beautiful view, yeah, it's not going to end nicely for you, most probably. So that's a fun thing about weightlessness and apparent weight versus real weight. So let's talk about Newton's cannon. So Newton is credited with discovering gravity. I mean, people knew that they weren't floating around before Newton. But the key connection that he made was looking at an apple, did not fall on his head, but he saw the apple fall at the same time as he was looking at a daytime moon. And he made the connection that it is the same force acting on the moon and the apple, but the apple falls to the earth, whereas the moon doesn't fall to the earth. It just keeps on moving around. So in order to explain this, he came up with a thought experiment. He would go up to a very high mountain where the air is so thin we can ignore air resistance, and he would fire a cannonball from this mountain. And the cannonball would do a parabola, as you would expect. But if he fired it faster, it would travel further horizontally before it would land. And it turns out that the Earth is not flat. So if he were to fire it fast enough, then it would curve at the same rate that the Earth curves away from it. And this is what we call an orbit. So, how fast would this cannonball have to be launched in essentially a low Earth orbit? So when we say low Earth orbit, you can assume it's grazing the Earth, but we ignore air resistance, in order for it to be in orbit. So let's have a look at some answers. I'm looking for 2 sig figs is my answer. Wolfstan's correct. Isabel is too low. Orla's too high. Evie's too high. Colton's correct. William's correct. Hassal's correct. This is different to escape velocity. Ileana's correct. Angelica, Eliza, Skylar sisters. Units, please. Clara's correct. Colton's correct. Tanishka's correct. T. Goel is correct. Loads of correct answers coming in here. Thank you for the units, Angelica, but too low. Correct from Ishita, Kara, Ryan, Timothy, Denadia, Pierre, and Owain. Isaac to 2 sig figs, I disagree with that. Ava's correct. So let's have a look at what's going on here. Miko too low. So escape velocity is a fun thing to talk about, but now that to calculate that, you essentially want to do a conservation of energy. Work out how much energy it would take to take the cannonball to infinity and then start it with that much kinetic energy. So in this case, it's orbiting. The only force acting on it is going to be its weight. We're ignoring air resistance and anything else. So its weight, given by Newton's law of gravitation, is going to provide the centripetal force. In this case, I'm interested in velocity, so I'm going to use it in this form. So I can rearrange for this. Big G, 6.67 times 10 to the minus 11, some random combination of units that I could work out, but I don't really care about right now. Mass of the Earth. If you don't remember the mass of the Earth, that shouldn't deter you, because you should remember little g. And then we can use little g in order to either work out the mass of the Earth, or we can just substitute for it, because little g is given by this expression. Oh. So substituting for that, we get very nicely that v is just the square root of little g times r. So subbing in there, we get our 7.9 kilometers per second. Pretty fast. Maybe surprising. So we get the same period for t as for when we're weightless at the equator. Ooh, same period. So there's something that Wolfson, you've reminded me of another question that I might ask at the end. Let's just have a little check on time. Oh, I don't think I will have time. Let's move on to this question. Apparently there's a part B, but I don't have it on my slide, but this is quite interesting. So let's go to the top of the Burj Khalifa, which is 828 meters tall in Dubai, 25 degrees north. You know what that means now. If I were to drop this on a windless day, it would not land exactly below where I've dropped it. Why? And how far away from the mark would it be? We've only got about 5 minutes. Colton's already answered this. Perfect. Ava, that's too far away. Oh God, is it because the Earth's spinning? You've spotted the pattern, Adam. Yes, the Earth is spinning, and that has an effect on all sorts of things. You can't get away from it. Nothing to do with fluctuations of air. Let's do it in a vacuum. Nothing to do with relativity. Coriolis effect. Ooh, I mean, it's related to it, but not really. Anyway, it's further than that. Angelica, it's not that far.
Justin, I lost track of where you were, and so I'm not able to answer someone's question in the Q&A because I was distracted looking up another answer. Someone
Okay.
has said, couldn't we just use the value of t from the last question, capital T?
Um,
But they asked that a couple of minutes ago, so I think it was before you moved on to the Burj Khalifa
okay.
one.
The 1.4 hours weightless, low Earth orbit. I think that would probably work out actually.
Great.
I think
Sorry,
it
I
would.
usually manage to keep up with you so that I can answer anything that comes through, and I just lost track of where you were, and
Yeah.
I had no idea what they were asking.
I mean, there's a slight problem that I think there's a part B in the workbook, but that's not on my slides. So if anybody's asking me about 2B, I'm sorry, it is not to be today. Um, Angelica, we've said too high. Denadia, it's further than that. Uh, Evie, less than that. There's no friction force from before. Yeah, there's no force on this penny, if you're talking about the penny. Emily's too high. Wow, Tanishka, that would be a really big effect. The answer is somewhere between half a meter and 1 meter. So if you're getting something outside that range, back to the drawing board. And a clear diagram is very key. Oh, Liliana specifying a direction as well. Arpith, that is very close to my answer, but it's not my answer. Give me two sig figs, please, Timothy. I know it's late,
Pretty
but
much
don't forget
perfect timing
units.
though, Justin. It is late, but we are at 7:59. So you can present your
Okay,
answer. Then we will send these lovely young people to go and get some rest.
lovely. So, uh, there's a diagram on the next slide that will make all of this a lot clearer. But essentially, at the top of the Burj Khalifa, you're going around a larger radius circle than you would do at the foot, which means you're traveling faster. So, if we fall from the top to the bottom without sideways air resistance to slow us down, we will now be traveling ahead of the ground because you have an initial horizontal velocity relative to the ground. So we can work this out, your speed at the top, so radius of the Earth plus this extra height, and here's that cos theta term coming in again. The diagram will make this perfectly clear. We can work out our relative velocity by subtracting the velocity at the top to the velocity at the base. And if I were to plug in numbers, it works out as about 5.5 centimeters per second. Now it becomes the Suvac question. All I need to do is work out the time of flight. So 828 meters, 9.81 meters per second squared. Plug in the numbers, it's about 13 seconds. So I times that 13 seconds by my horizontal relative velocity to give me my 71 centimeters. Let's have a look at the diagram, just so we can see what's going on there. So not to scale, of course, but let's look side on as a nice little cross section. So here's our radius at the foot, RB, our radius at the top, RT, and this extra distance here is going to be our height. So we can start plugging in some numbers into that. Let's move this out of the way so we can see. So in terms of those things, that's where that 5.5 centimeters per second comes from. So we don't actually need to calculate V top and V bottom and plug in numbers because we can simplify it algebraically. And then at this point, we can plug in numbers. So you're not going to make any intermediate rounding errors when you start subtracting those things. So stay in algebra as long as possible if you can. There's our Suvat again to give us our final answer. And that is us for today.
That looked like a popular diagram when that went up as well. We got a lot of reactions. Thank you so much, Justin. That was great. And I think it's always really lovely when we get to this point in the Preparing for the Pact course where we're really just trying to develop problem-solving skills and give you this boost at this point, wherever your physics journey takes you. This is our last session with Justin. After today's session, I will get the recording together and I will share the recording along with our final set of problems, problem set 4. I'm going to switch on the chat so that anyone who wants to say hi to Justin can, because I realised we were getting loads of thank yous through and they can all go through. Next week is a slightly extended PAT session. So anyone who wants to join us next week, we will run from 6:30 as usual, but we'll run all the way to 8:30 so that we have time to go through the solutions to problem set 4 and also to answer any of those last minute questions that you have. We'll be joined by one of my colleagues from the engineering department and one of my colleagues from the materials science department as well, just so that you can ask all the questions that you might have. We'll have full representation next week. But in the meantime, Justin, thank you. See you in 2026. And all of you have a lovely evening. Thank you so much, everyone.